I'm glad you're here. I'm going to talk about spatial coordination synthesis for augmented reality. I'm Mohsen Lesani from University of California, Santa Cruz. My collaborators are Yi-Zhen, Tsai, and Jiasi, Chen. All right, so you might have seen AR applications. You can maybe load a virtual object from the cloud on your screen. The latency for that is important. But more important is the latency of your interactions with that app. You want those to be very fast. And you can have multi-user augmented reality applications. For example, here we have a physical table and we have multiple virtual objects on top. And there are multiple users that are interacting with these objects. So what we want in these applications is first, low latency, and we want to avoid rollbacks because these directly affect the user experience. And we also want to make sure we converge to the same state. If you're moving the object and some other user is moving the object, we want to eventually have the same position. And more importantly, we want to respect the physical restrictions. Like, for example, this ball shouldn't go into the table, right? So there are physical restrictions. And there are sometimes user restrictions, user policies. If there are confidential information on a virtual object, maybe it shouldn't go out of the room. These we traditionally call integrity properties of the object. And so there are some approaches already. So there is one by Google that's shipped by the AR framework for Android. What they do is that they do most of the coordination on in the cloud. And so the latency is pretty high in this framework. There are also works like Netcode where there is an edge server, so one of the devices can be the server. But similar to the previous approach, they have an optimistic transaction processing or reconciliation. And a lot of time that leads to rollback. And so the user can see the virtual object going back. And so this community, including my group, has worked on hybrid consistency a lot, right? And we thought that this problem, when my colleague talked with me about this problem, I thought that we can readily apply a lot of coordination conditions that we have developed in the past. So that when we are close to the vase here, the physical vase, and we don't want to hit or go inside it, we actually coordinate because the location needs coordination, right? We want to coordinate only when necessary. But if we are talking about this location far from the table, maybe we don't need to do any sort of coordination. So we want to have hybrid consistency and benefit from the places where we don't need to synchronize. We don't need strong consistency. And my group developed this notion of coordination called well coordination. And we successfully applied that to relational schema. And we thought that we could readily apply it to these AR applications until we realized that's not true. And we had to devise new notions. So here, you're looking at this ball in the game, and someone is trying to move it to the right. The issue is that if someone else wants to move it down, and your action A1 flies to the other process, to the other device, and then you move afterwards to the right, what happens is that you're going to enter this restricted area that we didn't want to get into, right? So here, integrity is violated. And we say that A1, permissible right, conflicts with A2. It cannot commute past it to the right. And in well coordination, we had conflict graphs. So we would draw all the conflicts. And for this simple example I'm showing, the move method conflicts with itself. So we have a loop. What that means is that we have to synchronize all the time. We cannot do relaxed consistency at all. We should do strong consistency. We have to synchronize every time. And so that doesn't help us at all. It means that the application will be very slow. What we realized is that, again, this is very much dependent on the location. And well coordination had no notion of the current state. So we considered that. And if you look here, location L prime, there's no problem. You can move past A2. A1 can move past A2, and it's going to keep the integrity property there as well. So we want to be able to run them locally, and we do. So if the bar is very far from the table, these are the locations you can go without coordination. And this is something we captured in this new notion that we call well organization. But what do we do with the actions that are actually conflicting with each other? So I showed you one where A1 was conflicting with A2. What do we do in this case? well organization requires that either A2 commutes, which in this case doesn't, or we have to prevent them. We have to prevent these concurrent calls that are happening. And it might seem very hard. How do you control the other device? You don't have much control over them. Well, if they need to do the action only after acquiring some resources, and we take those resources, then they cannot do it anymore. And when I talk about the implementation, I get back to this point. The other thing that well coordination did was observing the notion of dependency, and it showed that it's actually dual to conflicts. Doesn't seem like to be the dual, but it is the dual. So here, so you can do action A2, and it's going to be fine only because you did action 1, right? So you didn't enter the restricted area. But look at the right side. We are maybe the other device, Bob's device, and we received A2, and we have not received A1 yet. So we do action A2, and we enter the restricted area, which is not good. We are violating the integrity. So A2 is dependent on A1, right? It doesn't permissible left commute with respect to A1. If you move it left, then integrity is violated. And we kept track of dependencies in the past using a generalization of vector clocks, which was very expensive. In this new project, we realized we don't need to do that. So if you receive the action A2, and you have no idea where the dependencies are, you can still check whether it's preserving integrity or not. And if it's violating integrity, you can simply keep it in a queue and wait until eventually all the other actions arrive, and there will be a state where action A2 is permissible, preserves integrity, and only then you can execute it. And this is much cheaper to do, right? You're not keeping track of all these complicated dependencies. All right, so we had this new notion, well organization, that relaxed well coordination even further, and now we had to implement it. What we did was that we adopted the escrow mechanism. You might have heard of this notion, but here there are so many things that we have to do on top of that. So here we have the ball at location 3 and the x-axis. We say there is 10 credits from one side to the other, right? So there are 10 credits. And from the location that you are, you need 3 credits to go to the left. There are 3 credits available for going left, and there are 7 credits available to go right. And so if Alice comes and wants to move 4 credits to the right, she needs 4 credits, right? And in this case, luckily, she has that credit, so she spends that credit and moves right. And the interesting thing is that, like energy, credits are preserved, right? So, but they convert from one state to the other. So when you move right, you create credit on the left. So, so that's new credit we get. But more importantly, how do we handle conflicts now? So you saw this issue that Bob is moving at the same time concurrently, and we got conflicts. What do we do about that? So it's not one axis anymore. We have to care about the other axis. We realized that to prevent this, if we acquire 5 credits from the down direction, then no one can take us to trouble, right? So before action A1, we have to collect enough credit and lock them. That's what we do. In this case, Alice doesn't have enough credit, so he first acquires that credit, asks others to give it the credit, and then locks it. So no one, like Bob, can now surprise us, right? And then we do the action A1, and only after everyone acknowledges they have done action A1, we release the locked credit, right? Only then we release it. So now that's good, because if Bob wants to do action A2, he realizes he shouldn't be doing that. He can observe the new state, and he doesn't do it. So I thought about locking, right? And immediately you might think, okay, what happens to failures? If a process fails, the credit that we have locked inside it will be locked forever, right? So that's dangerous. And I really thought that we cannot make it fault tolerant at the beginning. And reviewers insisted that you should make it fault tolerant. So we were forced to create. And we eventually did. So here's an example. So imagine all of these processes have 10 credits at the beginning in one direction, let's say D, and one of them moves two units in that direction. And there are some exchanges. As you saw, the protocol that I described has exchanges. So we have some exchanges. And suddenly process A crashes. So now what do we do? What do we know? How much credit did he have? What we can do is that we can have each process calculate how much exchange it effectively had with A1, with A. B calculates that to B2. Everyone else can calculate that, right? And they can communicate this information after the failure detector tells them that process A has crashed. And they can aggregate this, and effectively they have given him 1 credit. So now, at the very beginning, he had 10 credits. He used 2 of that sum, and then we gave him 1, so he had 9 in total. And we are 3 processes that are still correct. We divide it by 3, and each one of us recovers three credits. Now, the complication that arrives is that what if B crashes too? Now, well, with what I just described, we need information between A and B to be able to do the math that I described. But they have both crashed, and the information exchange between them is lost. So what we do is that we treat this whole set of A and B as a super vertex. And when we do that, we can still do the same. We can still calculate how much we exchanged with both of them together. C can calculate that, D can calculate that, and then we communicate that with each other. We can calculate the aggregate, which is 3 in this case. And then we say, okay, both of them together had 20. One of them used 2 because he moved by 2 units. And then we gave 3 to both of them together. So we sum that up, it's 21. And we have used 9 credit, we recovered 9 credits already. So we subtract that, it's very important. So we can now only recover everything together, but we remember how much we recovered before. So 21 minus 9, very important, we have to subtract 9. And then what remains for each one is a share of 6. So we have a lot of boards. We have 2D boards and 3D boards. And for each location and action, we have to know how much we have to lock, how much conflict we have with others. For that, we model this as in theory of linear arithmetic. So there is an action A, it's preserving integrity at location L, and there are some 2 other actions happening in other processes, action A1 prime and A2 prime, and they are fine, but when we do action A after them, we suddenly get into trouble. So we feed that into the SMT solver and ask what is the minimum magnitude for A1 prime and A2 prime that causes this trouble, right? And the SMT solvers can optimize for objective functions. They can tell us how much we have to lock to prevent this. So we did experiments on devices up to 7 and with different restricted zones, as I showed you. Our latency is the smallest because we can do a lot of operations locally. But the latency for netcode is much higher because it has to do at least 1 round trip of communication between nodes. We avoid that. Hambazi, our own tool, is even worse. Our past tool was even worse. It has to do 2 rounds because it does consensus for each action. So they have higher response time. And eventually, Firestorm is the worst because it has to go to the server and then come back in the cloud. So, and then we also experimented with different loads. We had a lot of different experiments. I get the chance to present some of them. So we increased the load, and again, the trend is very similar because we can do a lot of operations locally. Our response time is lower across the board. For throughput, because of all these coordination and heavy synchronization, for some of the higher workloads, for example, Firestorm and other previous frameworks couldn't finish the workload, but Hambazi did finish all of them. We also studied scalability. We increased the number of devices from 1 to 7, and we were consistently lower in response time. We also did fault tolerance, and the good thing about Hambazi is that it can continue to process actions even when failure happens, but Hambazi, when the leader crashes, then we have to go and change the leader before we can process anything. So in summary, I presented spatial coordination in multi-AR applications with low latency, convergence, and integrity. I introduced a new notion of well organization. I presented how we can implement it with a credit scheme. I explained how constraint solving can help us synthesize custom coordination, and I showed empirical results that show significant improvements in latency, throughput, scalability, and fault tolerance. Thanks so much for listening, and I think I have to take the questions afterwards. Is that right? Thanks so much.